Hey guys, welcome back to my channel, Logically Literate. In this video we're going to go over the changes I've made since the last code video. Those changes include a scoreboard update to show the weapons, health, power, angles, move, as well as some pop-up messages to say when damage happens and when it's a certain player's turn, as well as some timing adjustments to fix the timing of projectiles flying. So in the last video that you may have seen, the projectiles are going slow at the very beginning of the game, and then as the game goes on, the projectiles get very fast. So I had an issue with timing there. I also have added agents now, so I have a dumb agent on the right-hand side that does a simple algorithm, which I'll get into later, and then I have a smarter, potentially, agent on the left who is a deep Q-learning agent who's actually doing the machine learning for this project. Then we'll talk about the agent and how you actually can use an agent, as well as the asynchronicity of the DQN agent at training time. Lastly, we'll talk about the actual training script that's been written, followed by the logs and the graphs that I generate at the end of a training session, or at any point a training session is ended. So without further ado, let's go ahead and hop into the code, and we'll start going over all the changes since last time. So if you're familiar with my previous iteration of the code based on the last code review video that I did, you'll notice the scoreboard looks a lot different. So what I had to do was implement all of those tags you saw at the top of the screen, as well as the text at the bottom, and then the pop-up text that came up in the middle of the screen. Having static values is fairly straightforward. You create a label, give it a location, and then every single time the game iterates, you simply just call a draw command on the label and you render it onto the screen. However, if you want to show something as a pop-up that stays there for a couple seconds and then goes away, you have to implement a counter and then show it for a certain amount of time, decreasing that counter every single time you show it, and then removing it once the counter's over. That can be seen down here at the bottom. So I have a damage countdown. So when damage occurs, it puts at the very top middle of the screen, so-and-so has been damaged by this amount. And then every single time the game iterates, it decreases that counter by 1 until that counter is 0, and then message goes away. So we have two separate types of things that can be shown on the scoreboard. Essentially, I count the scoreboard as anything on the game that isn't terrain or tanks or projectiles. So the scoreboard handles all the messaging and all of the static values at the top. So to handle events like the end of the game, damage being displayed, the players who's active being changed, and just messages in general, I've created these functions here that essentially start the countdown timers for each one of these events. That way, when it gets down to this point, these trigger because the countdown is now greater than 0, and then they also start to count it down, and it shows it. At the beginning of the video, I mentioned that I was having a timing issue with my previous code. The get ticks from Pygame, as you can see here, pygame.time.getTicks, gives you the milliseconds since the game started. I was thinking I was calculating it properly by giving myself a delta, however I was not calculating the delta properly. So instead of calculating the delta of each iteration of the game, I instead created a static time step for when I want to render and slow it down versus when I want to go in headless mode and have it fast. And then what I did was I made the game run, but it passed that time step, the static one, into the actual projectile calculation. So the projectile flies at a constant rate no matter what. Whereas before, at the beginning of the game, the delta time that I was calculating was very small, but then as the game went on, it got very large. That meant the speed of the projectile was very slow at the beginning of the games, and it got a lot faster by the end of the game. So next you'll notice I added a folder called Agents. Inside of here we have the action enum, we have the state enum, and then we have a base agent. So the action enum describes all the actions that an agent can take. The state enum describes the structure of the state array, and the base agent describes the functionality that an agent has. So an agent can remember a move, it can act, which means if you give it a state, it'll give you a move to do. It can replay, which is used for training, and it can load and save its model if it has one. It also has a memory that has a length of 2,000 points. So it can only remember the last 2,000 moves that occurred. One child of the base agent is the dumb agent. The dumb agent is player 2 on the right-hand side that you see in red. It essentially is this one act function. And all it does is it takes an initial shot, and then once that shot lands, it begins to walk the shot in towards the enemy with random amounts of walk in the direction of the enemy. So if it overshoots, it'll random walk into the enemy. So essentially what it does is something like this when it's shooting at the enemy. Eventually, the dumb agent will kill you if you don't kill it in time. So it's very easy to beat the dumb agent unless you're a DQN agent that does random stuff that doesn't make any sense, and you get shot quicker than your randomness allows you to shoot the other player. So that brings us to the DQN agent, the star of the show. His name is Daquan. Daquan is a deep Q learning network. Daquan has an epsilon. As more games are played, epsilon is decayed. Epsilon is what gives you your randomness. So when epsilon is large, your actions will be very random. As epsilon begins to get smaller, meaning you're playing more games, so as you play more games, you start to trust your model more. You use your model then to predict what actions you should take instead of giving random actions. At the end of every game, replay will be called, and you will take a batch of your memory and you will replay or learn and retrain that model that you use to predict when you act. So essentially at the end of every game, you take your memory and you see what was good, what was bad, you remember it, you put it into your model, and then you play the next game. Daquan also has functionality to load a model and to save a model. So when Daquan is in player 2 mode, he'll load his model and you'll be able to play against Daquan. When Daquan is in player 1 mode, he'll save that model after he trains and fits a model to the game. Now because I have a game, and me as a human, I play it asynchronously, meaning the game continues to play and I interact with it, I inject actions into it, and then once the game gets to the point where it checks for actions, my action takes effect. I needed a interface that would allow me to play the game asynchronously as a DQN agent, just like I do as a human. When you use something like OpenAI Gym, it's a synchronous interface from what I understand. So there's an act function, and the act function returns the next state, the reward, all that stuff that you need for your deep learning to be able to learn. I'm not able to do that because of how I architected this. I wanted the agent and I wanted the training script to be separate from the actual game itself. That way the game was still playable by a human, and it wasn't just do one iteration, wait for an input, do another iteration, wait for an input. The way I implemented that was with a callback system. However, since I'm using threads, I have to use locks. So if we go back to main, you'll notice that I have a lock around the actual main loop of the game. That way I can enforce that do an action, wait, do an action, wait mechanism. And the main way that works is I have a class called trainer. Trainer is a script that does my actual training for my algorithm. So at the top I have some configurable hyperparameters. Then I have this handler, which is essentially my thread synchronization tool. Create a handler, and then I actually create a game in its own thread. And then I start the game. From there, I generate a DQN agent who will essentially interface with the game similar to how a human interfaces with the game. So it won't be pressing keys, but it'll be sending in commands that emulate pressing keys. Then I create a data logger so I can actually log off every single step of a game and every single game, the different outputs from that game. At that point, I initialize some variables just so I can track some data throughout the training session. And then I actually tell the game to restart, and I start iterating over the number of episodes. So an episode is a game, and at the top I set how many games I want this DQN agent to learn against. Then I do some more kind of timing and metric collection. I show a message on the screen, which is what you see in the bottom left-hand corner, and then I start the game. So while the game's not over, I tell my agent to act. I get that action. Then I tell the game to queue an action. This queuing of the action happens inside of main.py. It first grabs the lock, so it synchronizes the thread that makes the call with the game thread. Once it attains that lock, it queues up an action, and then it sets some variables so the game knows how to use that action. Once it makes the action, it sits in this wait for callback. So you'll notice above I said I had this handler. So the handler has two functions. One of them is wait for callback, which you see here, and the other one's callback. So callback is passed into the application when the game is started. Callback is what happens when the game is done stepping through one step of the game. So one step is either you do a non-fire move and it goes through, moves the game state, and then tells you that it's finished, or you do a fire move, in which case your tank will fire, then the other tank will modify what it needs to, and then fire, and then the game will be finished. So a step could be a one move, or it could be a fire on your side with multiple moves and then a fire on the other side. When we are waiting for a callback, it's a glorified while loop that, again, grabs the lock. This time it's a different lock. This lock is local to the handler. But it grabs the lock, and if that callback was ever called, if it was triggered, then it breaks out of the loop, waits a very small amount of time. Oh, it doesn't wait. It breaks out of the loop, and then it returns the next state, the reward, and the game over Boolean. This return here looks a lot like OpenAI Gym's return on the act function. So that was the reason for doing that. I wanted this to kind of flow like OpenAI Gym. That way I could use training algorithms based on OpenAI Gym. Much easier. At that point, I do a remember call for the agent. I log off the step of the game. I save the next state as the current state, and if the game's over, then I display some things. If it's not, then I just play the next iteration. Once a game ends, we print out some metrics. We also log the game itself. So we're logging who won, how long it took to play, how long it took to train, what was the value of epsilon that iteration, what was player 1's health, what was player 2's health at the end of the game, what was player 1's win ratio, and player 2's win ratio at the end of the game. Win ratio is a sliding window. The reason being, if at the beginning, the first 100 games, you have a win ratio of like 1 to 100, so it's like 0.01. But then 1,000 games in, that 100 game win ratio window is now 10%. You can tell that you're improving because this window over here, the very beginning, you were really bad, and this window over here, you're getting better. Similarly, if you step ahead another 1,000 and your window is now 50%, you can see an increase from the sections of the games that you're playing. However, if you get to a point where that window starts to drop off, you know you're actually doing worse now. And if you see it continue to drop off, you have a way to pinpoint exactly what model that you saved will be the best model. So that leads us to, we save the model every 50 games, or every save period games, which happens to be 50 right now. We save off this winners object, and then we play another game. However, if we get a keyboard interrupt, a Control-C twice, that will end the game, and then it'll also end this for loop of training. And at that point, we can queue an action to actually tell the game to end. Once the game ends, we then come over here, and we say write the object that is inside of the logger, so the logger data, to a file. It writes it to a file, and then we show the graphs. The graphs are just matplotlib graphs, so that kind of takes us lastly to this utils folder where I have a very simple class. It's JSON based, so it's got a dictionary inside of it that has some data in it. We can add a step, which means every single time the game steps we can save off some data. We can add a game, so every time the game ends we can add some data. We can add anything that just adds stuff to the top here. Actually just adds something on the top level. And then we can actually save it to a file, and then we can draw some graphs. And right now all I'm showing as a graph is essentially the amount of wins at any point in the game that a player has, which is a line graph. And then after that, I show player 1, player 2's wins versus games. So we can kind of see how they increase over time, if it's linear, if it's exponential. I have epsilon over time, so I can see like, okay, epsilon was at this point, and this player started getting more wins. So obviously it was using more random data it was using more real data versus random data. And then lastly, I show the player 2's health versus the game. So the idea with that is if their health is very low most of the time, then that means I know that I'm very good with my shots. It just happens to be that I'm not fast enough and they're killing me quicker. However, if we see more of them situated at the top of the graph, meaning their health was higher at the end of the game, then that means that the DQN agent was doing worse because most of the time the player was never hit. Really, that should be kind of a histogram or something, but right now it's just a line graph with dots. So if you see a whole lot of dots at the top, then you know you're doing bad. If you see a whole lot at the bottom or in the middle, then you know you're doing average. If you see a whole lot at the bottom, then you know you're doing very good. So that pretty much covers it for all the code changes. I know that was probably a really long video, but that covers everything. So if you liked the video, go ahead and hit the like. Leave a comment if you have any questions or suggestions. Also check out the link down in my description for my GitHub where you can download this code and you can play with it yourself. It's relatively plug and play. If you have any questions about anything, again, let me know. But until next time, thanks for watching and have a nice day.